Welcome to Session 10 of Dr. Donald J. Wheeler's Understanding SPC seminar. This session will look at what constitutes world-class quality and see how it differs from the traditional ideas about quality that have come down to us from the 18th century. This concept of world-class quality will be illustrated in the way one company uses a process behavior chart for continual improvement. This session will primarily come from Understanding SPC, where we begin on page 144.
Variation always creates cost. Actions to take to deal with variation after the fact will inevitably increase costs. Actions that reduce variation at the source will simultaneously reduce the subsequent cost while increasing product quality. The further upstream you can work to reduce variation, the lower your cost of variation will be. Now, on the next page, you have a loss function for the conformance to specifications concept of quality. As long as we get to ship it, we don't have any excess cost. If we have to rework it, well, that's an excess cost. If we have to scrap it, yeah, that's an excess cost. But if we don't have to scrap it or rework it, if we get to ship it, then it's out of here. No problem. Until it gets to your customer. I once heard one CEO sing the praises of his suppliers by saying, all of our suppliers are no damn good. Now, what did he mean by that? Were the suppliers sending him bad stuff? No, the suppliers were sending him stuff that met the specs. But you really don't have a uniform loss function. You've got, well, we know, in terms of excess cost, we know three things. Figure 6.622. We know the excess cost of scrap. We know the excess cost of rework. And by definition, if you're right on target, there's no excess cost. So you really know excess cost at 3 points. And all of our experience with the real world has taught us that continuous functions do a better job of approximating reality than do step functions, at least above the quantum level. And so if we pick a quadratic, with 3 points define a quadratic, so about the simplest curve we can put in here would be a quadratic equation inside the specs. And this loss function provides a first order approximation for any more realistic loss function we might choose. Now, I could go through the Taylor series expansion and talk about how we get here, but that's all advanced calculus. But nevertheless, advanced calculus, 250 years old advanced calculus, tells us you're going to end up right here. So might as well just start here. So if we have this loss function, then the average excess cost of production and use, making it and using it, would be the integral over all x of the loss function times the probability distribution integrated relative to x. So the actual cost of production and use would be the nominal cost of production plus the average excess cost of production, that's the scrap and the rework, plus the average excess cost of using the conforming product. So on page 147, if we have a probability model and a quadratic loss function, and we multiply the two together and integrate over all x, we have the average excess cost of use. And I don't care what probability model you might plug in, this integral has the following form in every case. K is a constant that converts it into monetary units, usually yen. Sigma squared, of course, is the variance of the product stream. And mu minus the target is the bias. How far off target are you, squared? So this average excess cost of use will be minimized only by operating on target with minimum variance. Now that is the new definition of world-class quality. I hate to say new since it's been around for over 60 years, but it's still the definition of world-class quality, and you'll see that in a minute. So world-class quality requires no less than operating your process predictably and on target. Minimum variance equals predictable. So conformance to specifications, zero defects, Six Sigma quality, cost of quality, and all other specification-based nostrums completely miss this point. World-class quality has been defined by on target with minimum variance for the past 60 years. The sooner we wake up to this fact, the sooner we can begin to improve our competitive position. So how do we deal with that? Well, the average excess cost of production and use can be estimated by K times the mean squared deviation about target. The mean squared deviation about target is sigma of X quantity squared times the X double of R minus the target quantity squared, the variance plus the square of the bias. Once we have that, the K value that converts everything into into monetary units is the cost of scrapping an item divided by the point at which you scrap it, one of the specifications usually, minus the target quantity squared. With those two values, K times MSD is your average excess cost, so the effective cost of production and use will be the nominal cost plus the excess cost over the nominal cost. I'm going to illustrate the formulas here on page 148 with an example. And we'll start at the very beginning with the capability and go all the way through. So the following example is going to summarize chapter 6 in one example. I'm going to ask you to turn in the textbook, page 156. And don't panic, you don't have to read Japanese. You may read more Japanese than you know. What can you tell me about this process? From this chart right here. Is it being operated predictably?
Yes.
Yep. Yep. Predictable.
What's the subgroup size?
4.
As I said, I'm going to walk through the whole scenario, and you can scribble this in the margin around this page if you want to with me, or you can turn to the front of the or back of the book to a blank page, whichever you like. But this is going to be an analysis and interpretation of page 156. So N is 4. If down at the bottom of page 156, the grand average is 15.899. And that's millimeters. And the average range, 0.304 millimeters. Can you find that? Down at the bottom of the page, right there in that little box. So sigma of x will be the 0.0304 millimeters. Subgroup size 4, our D2 factor is 2.059, I think, inside front cover of the workbook. You can check that. And so I get a 0.0148 millimeters per standard deviation. The 2.059 is in standard deviation units. Now, what kind of high-tech product do you think they're making that has a standard deviation of 15 microns? 15 thousandths of a millimeter. Got any ideas? Turn back one page. Page 155. Yeah, this is a cigarette lighter socket. Actually, socket's a bit of a mistranslation. It's the outer shell of a cigarette lighter itself. It's a piece of mild steel punched into a cylinder with a flange on one end, and then a crimp is rolled in it, and we're measuring the dimension from the back of the flange to the back of the crimp. One guy at Ford said, this is the only critical dimension on this part. If this dimension isn't right, you have some pretty bad failure modes. The thing sticks in the socket and catches the car on fire. The thing pops out of the socket so forcefully that it lands in somebody's lap, and you have a wreck, and then the car catches on fire. In other words, there's some pretty bad failure modes associated with fire inside a car. And this is what this dimension affects. Now, up at the top of the chart, you see the specs? (15.9) plus or minus 0.1. So our lower spec limit is 15.8 millimeters, and our upper spec limit is 16.0 millimeters. So, what about our capability? I'm not going to worry about the continuity correction factor here. Sometimes we ignore it, just use the upper and lower specs. And I'll just do that here. So, 0.200 millimeters divided by 6 times 0.0148 millimeters. That's 0.2 over 0.0888 is 2.25. Good enough? So they've got a capability index of 2.25. The specs are twice as wide. The space available is 225% of the space required by this process. That sounds pretty good, doesn't it? DNS 15.899 is just barely closer to the lower spec than the upper. So distance in error spec 0.099 millimeters. So twice the DNS. Over 6 times 0.0148, 2.23. When your CPK gets to be close to or equal to C sub P, you're pretty well centered. So they're set predictable, they're centered, and they're capable by a mile. This process is clearly deep in the ideal state. Now, what is their effective cost of production and use? Well, let's start with the formulas here on page 148. The mean squared deviation about target, sigma of x squared, plus the difference between the average and the target. Now, here, Mike, I'm going to assume the 15.9 is the target. That's the way they stated the specifications. That's all I can go on. So, 0.0148 millimeters squared plus the average 15.899 is 1 micron, 0.001 millimeter off target. And so this is 0.0002220 millimeters squared.
This average minus target, how will it is then 2.001? Can I explain to you?
Yeah, that's the 15.899 minus the 15.9.
Oh, okay.
And that is, you know, whether it's positive or negative doesn't matter since I'm going to square it. Now, I want to make up a number here. It's not on the chart. Let's say the cost of scrapping an item is 20 yen per piece. This is a very simple little part, probably 20 cents or 20 yen is about right. but you're going to see that that number comes out in the wash at the end, so it's really immaterial, but I have to have something to do the calculations with. So K is the cost of scrapping an item, 20 yen, divided by the target, 15.9, minus the lower spec limit, 15.8, as I'm assuming that if you go outside of the specs, you're going to scrap it, and that distance squared. And that is 2,000 yen per millimeter squared. $2,000 per millimeter squared.
Why do we use the lower spec limit in this case?
I could have used the upper.
Okay.
Either one. I'm just, for purposes of discussion here, we'll assume that everything that's non-conforming gets scrapped. That's an assumption. It's probably not a bad one. So our average excess cost is K times the mean squared deviation about target. Take the 000220 times 2,000 yen, the millimeter squared cancel out, and you end up with 0.44 yen per piece. 44 hundredths of a yen per piece. That's the excess cost. That's, in this case, since they really don't have any scrap, they don't have any non-conforming. This is the cost of variation. The cost of things not all being exactly alike. So the effective cost of production and use is 20 yen plus 44 hundredths of a yen divided by 20 yen, which is 1.022. Their excess cost here are running 2.2% of production. So if they could wave a wand and make everything perfect, the most they could hope to save is 2%. They don't have a lot of excess cost here. And their customer at the next department, when they turn this shell into a cigarette lighter, don't have a lot of trouble using the parts. So they don't have a lot of excess cost of production. They don't have any excess cost of production, and they have very minimal excess cost of use. So their total excess cost, 2.2%. Now, let me save you some.
Dr. Wheeler, so
Yeah.
in practice, where does this 2.2% cost comes from? It comes from the variation, but what does it really mean?
Comes
in
from
practice?
all of our suppliers are no damn good. It's the gyrations you go through to make the conforming product work. I learned a long time ago, do not assemble the toys on Christmas Eve. Because if something doesn't fit, you're in trouble. It's supposed to all fit together, but it doesn't always all fit together, does it? You see, the chaos created by parts that are just in spec, but don't really fit together. We'll talk more about that when we get into this afternoon. But it's the excess cost of use. They get to ship everything to the next department. But when you start assembling the parts together into a cigarette lighter, things don't always go smoothly. And so they have a very little bit of excess cost here, 2.2%. Now, I'm going to save you some time and trouble. Get the reducing production cost book out. Turn to page 171. Okay. In the reducing production costs, we're looking for page 174. There's a column where C sub P is 2.3. Go down to the row where CPK is 2.2. And there's your effective cost of production and use. Now, actually, we had a 2.25 and a 2.23, which is kind of in between these two numbers on the diagonal. And if we interpolated, we get our 1.022, which is what we just calculated. You see, once you have the two capability indexes, you have all the information about the process and the specifications, and this number can be looked up in a table. Table 1 is for everything getting scrapped. Now, about that 20 yen per piece, what if I'd chosen 40 yen per piece? Well, this would be 88 hundredths of a yen per piece, and this would still be 1.022. So this is independent of that cost. We're going to go through this book and learn more about the tables in this book this afternoon.
Now we return to the chart from Tokai Rika on page 156 of Understanding SPC.
So, back on page 156, they don't need to improve this process. Their excess cost of production and use is only 2.2%. They're capable, they're predictable, they're on target. And yet they're going to take this process and improve it. So you figure out how they improve this process, and you'll figure out how to improve your processes. On page 155, you have a part of the chart itself, and they're going to get 4 pieces a day, 1 piece at 10, 1 at 11, 1 at 2, and 1 at 4. That's not a lot of data. They're making 17,000 of these parts a day, and they're going to measure 4 of them. That's not a lot of data, is it? How can they get away with 4 out of 17,000 pieces and 1 subgroup a day? Well, they asked themselves that question. You see, this is the beginning of a model year. They just came back from summer vacation, and they're getting geared up to run for the next model year. And they go back and look at the chart for July, which we don't have. And on that chart, the range chart's okay, but they had 16 out of 25 points out of control on the X-bar chart. Therefore, the present measurement method can detect process change. As long as you have enough data to detect when the process changes, you have enough data. So they're going to continue to collect 4 pieces a day and 1 subgroup a day, because this process, when it does go north or south, it tends to do so over a period of several days. So it changes slowly in most cases. So here's the histogram of 3 months of their data. And you can see the capability of 2.25. They could literally put the process beside itself twice and still fit inside the specs. Well, then around the 25th and 26th of September, we have a couple of points outside the limits. They don't just circle the 2 points outside the limits. They circle the whole run leading up to those 2 points. They know they have a problem on the 25th and 26th of September. They might have had a problem as far back as the 17th of September. So they would say you got 1, 2, 3, 4, 5, 6, 7, 8 points out of control. Well, you only have 2 outside the limits. Going back to the last time you crossed the central line broadens your horizon and gives you a bigger region to look at when you go to look for the assignable cause. You ask what happened on the 25th and 26th of September, you may not get an answer. You ask what's happened since the 17th, you're more likely to get a reasonable answer. So, abrasion on the positioning collar, a diagram of it. This is the part that gets the tool wear in this case. There are 2 steps that are being tracked by this process. The first step is called blanking, and it's where they punch the mild steel disc into a cylinder. The second is called rolling, where they put the crimp in. We'll hear about both of these. So here is the shell. Here's the positioning collar. Here's the outer roller that puts the crimp in. The pressure pad holds the shell against the positioning collar while the roller does its job. What happens the very next day after this out of control point? They're right back on the target. How'd they do that? They jury-rigged it, placed the worn side on the back. Emergency action, reverse course collar to use unabraded side while they're waiting on a new collar to come in. Wherever possible, they take action to get back on target because they're operating with the idea of on target with minimum variance as what is desirable. Well, they put a new collar in a couple of days when it comes in, and so they take occasion to calculate limits after they get the new collar in. Here on page 164, they run along, and then on the 27th of October, no long run this time, just bang, they're outside the limits. X bar suddenly out of limits. So they start digging. Some defect must have occurred to the process. Investigation done. No defect found at rolling. Must be at the previous step. Ah, here it is, wrinkle on the flange. So over the weekend of the 15th and 16th of November, they repair the die and improve the bolt for the pressure pad. They calculate limits backward pro forma but they start collecting data for new limits after this change. And so they finish up the year predictable, capable, on target. We'll say it's on target. They're a little off. And happily producing 17,000 good pieces a day. Then, after the New Year holiday, we get 4 points above the upper limit. And they circle a run. Ordered a new positioning collar for now okay to continue production. They're going to upgrade the tooling, and so the special tooling is going to take some time. So here they let it run, knowing they're not in danger of going out of spec. Then, February 24, the new collar comes in. They put the new collar in. Change positioning collar to TD processed 1 to increase abrasion lifetime. Probably a tungsten coated part. Positioning collar changed at rolling operation. Here's their setup, the part and a shim. They collect data following that. They calculate the limits. Notice they use the same symbols we do. They ought to. We taught them how to do this. What's happened to our bar? It was 0.0304. Now it's
Average range has dropped.
0.0207. They have cut the variation by 1/3. Yeah, by 1/3. Now, a standard deviation is 10 microns. Look at the data. Can you read it? The data are given in reducing production cost at the end of chapter 2, and you can actually read the data there because I transcribed them. The data are given to 2 decimal places. So the measurement increment here is 1/100th of a millimeter. And the standard deviation is now 1/100th of a millimeter. When you get the standard deviation down to the same size as the measurement increment, you've gone about as far as you can go in making things reducing the variation. Now, this is no flash in the pan. They're going to continue operating at this level of variation for the next 13 months. The rest of the record as we have it. Now, how did they do that? Did you see it happen? How'd they reduce the variation? I don't think that they were trying to improve this process. They didn't need to. There was no economic incentive. There was no production pressure. And there was no competitive pressure. 17,000 cigarette lighters is enough to supply all of the assembly plants in Japan each day. That's market share. They own this market. There's no pressure, but they could because the chart told them what to do. They're a little bit slow to respond. Back there in September, there were 2 points out before they circled the run. In October, there were 3 points out before they circled the run. And in January, there were 4 points out before they circled the run and started taking action. But when they circle the run and start taking action, they don't quit until they find something to fix. Now, their capability indexes are up around 3.3. And they're running right down the middle lane. That brings us to April. April is boring. 17,000 good pieces a day, predictable, capable, Ho hum. Good times are great to live in, but they sure make for dull reading. And they worked happily ever after. Only one thing of interest on April. What's happened to the specs?
Go wider.
50% wider. No note about that. It just happened. Does it matter to Tokai Rika? Now their capability indexes are up around 5. And they're going to run right down that middle lane. At this point, a GM vice president asked, didn't it cost more to make the parts that good? No, this is what their process is capable of making. They're not satisfied with it doing anything less. It actually costs time and trouble and money to make things worse. This is what their process is capable of delivering, and that's what they're going to get out of it. Well, a little bit of excitement here in May. See that 4? That's out of control report number 4. Every time this thing goes out of control, they have to write a report on what they found. Wrinkle on the flange, correction, increase the pressure on the pressure pad. Out of control report number 4 issued. No differences in new and old lots of steel. A few days later, the problem comes back. Wrinkle on flange due to variation in blanking operation. So work on flange to adjust blanking dies cutter. Dies varied by 0.12 of a millimeter. Adjustment complete. And who did the work? There's his initials. You see, this is the process log. Everything, the data, all and the corrective actions, everything is right here on one page. And if you want to find out more about it, you read the out of control report number 4, you go out there and look at the book, and you can see all the rest of the context for that report. Well, write down lot change on the report to supervisor on anything that's abnormal, just boring, oh-hum. Then in early July, a point above the upper limit. Cannot find the cause. Is it due to positioning, collar, abrasion? So here, since they can't find anything to fix, they fix the chart. They revise the limits upward to fit the running record as it runs along, still 100% conforming. Then it goes above the limits again in September. And this time the note is definite. Due to abrasion on the positioning collar, it's time to order a new collar. So they order the new collar, and it comes in on October 5. And it looks like everything just goes to pot here because it was getting hard to see the graph. So they actually blow the scale up. What used to be 10 units is now 4 units. So they made the scale 2.5 times bigger on the X-bar chart. They put the new part in, change the position and collar, life of collar 224 to 10.5, 2.9 million parts. Necessary to change collar once in 4 months. Wait a minute, they just ran this part 7.5 months. Why are they going to change it in 4 months? Going back to the chart. In March and April and May and June, there was no problem at rolling. But beginning in July and September and October, there was that slow upward drift. So they're going to replace the collar before the tool wear can start in. Send us a collar the 1st of February. We'll need it then. Now hang on here. The specs are 30 standard deviations wide. The capability index is 5. And they're going to change the collar once in 4 months. They're going to allow 0 tool wear. How do you explain that? The only explanation that fits the facts is on target with minimum variance as a way of operating. Another thing we can see here, look at the handwriting. 1, 2, 3, 4, 5, 6. There are up to 8 people keeping this chart. That becomes important later. Well, see, as Ko Yoshida told me one day, here in the US, we're just concerned with what is acceptable. So we draw the line, this is acceptable. Sometimes we raise the bar, 1.33 capability, 1.67 capability, even a capability of 2. We're still drawing the line. That's the finish line. Get there and you've got it made. He said, in Japan, we're focused on what is desirable. That's on target with minimum variance. And it's a completely different concept than what is merely acceptable. This is world-class quality. This is just arguing about how good the parts have to be. Well, a question mark looks the same in Japanese as it does in English. Can't always find the cause. So here's a point out, loose bolt on positioning collar, and he draws a diagram. Right there, that's the bolt that's loose. So the repairman will know what to work on. Point out here, cannot find the cause, board thickness is okay, collar is okay, pattern is okay. Why does he take the time to write what he does not find? Look at the handwriting. This is a note from one worker to the next. Yeah, I know it's outside the limits. This is what I checked. The new guy continues the long run, doesn't he? I don't know if I can do it. The thumb of that hand is right there at 15.9. The central line for the chart is no longer at 15.9. And the clue we have as to what's happening comes on the note for December 15. And it's very strong. It's in Japanese, it's kind of like Dubkov, we haven't been writing the smallest observed value. Be sure to write the smallest value down. A part like this, typically, you put the part in a measuring device and you turn it around. As you turn it around, the readout will vary. And you take the max and the min and write the average of the two. That's typical for this kind of part. Now they're going to change from writing the average of the high and low to writing the minimum. That's a change in the way you measure the part. We talked to Mr. Matsui about this, consult with management about this. We're supposed to be measuring the part differently than we used to. And this is the analysis after everybody is recording the smallest value. By the way, our bar is still 0.0225. And so when everybody gets on board with the new measuring system, we have another downward shift in the running record. and a downward shift in the limits, because that's both of this. This is, I think you have old measurements with limits that are partially based on old measurements and partially based on new measurements. The word came down to make the change here, but not everybody got the word. So some of these were old style, some were new style, and we start getting limits that are based on a hybrid. When everybody gets on board, we get the limits recentered around the new running record. The average is 15.88 instead of 15.9. Now they're measuring it, everybody's measuring it the same way. And that brings us down to February, when right on schedule, they changed the positioning collar. What's different about this change from all the preceding changes? They're changing the part before the part can change their process. We'll need a new part on the 1st of June. Send us one then. And that brings us down to March 12, when Larry Sullivan and his friends from Ford Motor went through the plant at some time between 2 and 4 in the afternoon. They saw a group of 8 workers gathered around this chart, engaged in animated conversation. So their way of thinking, that spelled a problem. There was some trouble. So they asked their host what was going on. Their host went over and inquired and came back and said, it's a routine review of an ongoing chart. And to make it clear that they weren't sweeping something under the rug, they translated the chart and photocopied it, gave us the whole 20-month history before they left the plant that day. This process has been in the ideal state for the past 5 months. It's predictable, it's way capable, and it's certainly on target, especially given the shift in measuring technique. This is what world-class quality looks like. Now, if they do this with a cigarette lighter socket, what do they do with something that really matters? Well, Ford had a chance to find out. Their 1983 Escort transaxles were produced primarily at Batavia plant in Ohio, but a certain proportion of them were outsourced to Mazda. Same blueprints, same specs, same application, Japanese fabrication and assembly versus US fabrication and assembly. Now this was a hush-hush project. Took everybody about 3 years to catch on to it. At the end of the model year, they could see the warranty costs of the Ohio transaxles were 10 times greater than those of the Japanese transaxles on a per transmission basis. They only had twice as many claims for the US, but 5 times higher costs per claim. So they took 10 Ohio transaxles and 10 Japanese transaxles, put them on the test stands, tested them, then they tore them down, and everything that had a specification got measured. They put out a videotape on this, and I inherited David Chambers' copy of this. You couldn't buy it after a while because GM bought too many copies, so Ford quit selling it. The Ohio transaxles met the specifications, but on the videotape they said overall the histogram was described as filling up the specifications. But they went on to put a weasel word in there. They said, on the critical characteristics, we only used about 70% of the specs. Overall, the Japanese transaxles took up 35% of the specifications. And on the critical characteristics, the Japanese transaxles only took up 25% of the specs. On a transaxle, on an automatic transaxle, the heart of the transaxle is the valve body. And then on the videotape, they actually show the technician testing the valve body. The valve body is just the bottom of the transaxle where all the hydraulic valves are positioned. So you have these holes with valves that go inside them. So he's measuring the bore on each of these holes on the valve body. He puts it over the probe and he turns it around and he sees the run out, the out of roundness to a 10,000th of an inch. He got to the Japanese transaxles. He started measuring them. He said, my gauge is broken. There's no run out. To the 10,000th of an inch, he couldn't measure the out of roundness. So the gauge maker came in, checked the gauge. It was fine. It's just that these 10 parts were so alike, he couldn't detect the difference. That led the vice president of powertrain, John Betty, to put it this way: while we were busy arguing about how good the parts had to be, they were working hard at making all the parts exactly the same. The Ohio had the center cut approach. Make enough stuff, some of it's bound to be good. Burn the toast and scrape it. Japanese, on target with minimum variance. World-class quality is defined by on target with minimum variance. The only way to operate with minimum variance is to operate predictably. The only way to establish and maintain predictable operation is by means of a process behavior chart. Everything else is just wishful thinking.